Hey guys, it's Mr. Wolfe here, and I'm going to be going over differentiating between mass and weight. So let's first start with mass. What is mass? Well, mass is going to be the amount of stuff, the amount of atoms, the amount of matter in an object. And it's also important to recognize what mass is not. And mass is not volume. And so when I say it's not volume, think of a pillow compared to maybe a dumbbell, something you might lift at the gym. And the pillow is going to take up more volume, but we know that that dumbbell is going to have more mass, more matter, more atoms in it. And so we cannot equate mass with volume. They're not the same thing. So mass is also not going to be weight. Now the two are related, and we're going to go over that in just a second. All right, so mass, again, it's the amount of matter in an object, and its unit is going to be the kilogram. And we can abbreviate kilograms as kg. All right, so that's mass, but what's weight? Well, let's say we take a mass, maybe a person on the earth. Well, since he's on the earth is going to be pulling down on him. And the force at which the earth pulls down on this person, that's going to be that person's weight. It's going to be the force of gravity on an object. And so since weight is a force, we're going to measure, like we do all forces, our unit is going to be the Newton. And so we're going to get to this area in just a sec. But before we do that, let's look at this box down here first. So this box is going to give us an equation showing us the relationship between mass and weight. And so our force of gravity, remember, force of gravity, that's just weight, is going to be equal to mass. But remember, they're not the same thing. So what's going to help us differentiate the two is going to be the acceleration due to gravity. So we're going to get more into what acceleration is in the next unit. But for the purposes of this unit, think of the acceleration due to gravity. That's telling us how much this planet is pulling on this mass to give us our force of gravity or our weight. And so we could go back up here and we could say that our weight is determined by the acceleration due to gravity, which we could abbreviate again as a little g. All right, and so this acceleration due to gravity, since we don't have enough room, this changes depending on location. All right, and so what do I mean by this? That the acceleration due to gravity changes depending on location. Well, this is going to be the reason why people weigh less when they're on different planets, right? People on the moon could jump higher because they weigh less. And so let's go over an example looking at these three planets, and I know the moon's not a planet, where we have the same person, all right, and on each planet. Now, the amount, his mass, the amount of matter, the amount of atoms that make up his body, no matter where his location is at, is not going to change. So we could say that his mass is the same at all locations. That's not going to change. What is going to change is how much these planets are pulling on the person. And so the larger planet you have, the more it's going to pull on this person. So Jupiter's going to have the largest force of gravity, followed by Earth, and then the moon. And for now, we can represent that pull by using the acceleration due to gravity. And so the acceleration due to gravity on Earth, and this is just something to remember, is 9.8 meters per second squared. And since the moon's going to pull less on this person because it's a smaller mass, the acceleration due to gravity on the moon is going to be 3.67 meters per second squared. And then finally on Jupiter, since it's the largest planet, its acceleration due to gravity is going to be 26 meters per second squared. Now, our acceleration, this is going to be a vector quantity, and all these planets are pulling down on our person. And so since they're pulling down, we're going to say that they're all going to be negative to specify direction. All right, so here's an example. We have the same person on all planets with the same mass, but each planet's going to be pulling on him with a different force of gravity, represented by our acceleration due to gravity here. And that's going to give him a different weight on each planet. But let's actually calculate his weight on these planets. So, and let's give him a mass. His mass is going to be 75 kilograms. All right, so let's find this person's weight on Earth. All right, well, we know that weight is really just equal to the force of gravity, and our force of gravity is just mass times the acceleration due to gravity. So our mass is going to be 75 kilograms, and our acceleration due to gravity on Earth is 9.8 meters per second squared. When we multiply these two together, and remember it's negative 9.8 meters per second squared. So when we multiply these two together, we're going to get a number that's negative 735 newtons. And this makes sense because this is a force that's pushing you down on the ground. So that direction does make sense. So let's look at this person's weight on the moon. And even before doing this calculation, we know that it's going to be less than 735 newtons because our acceleration due to gravity is less. So our force of gravity, our weight, is equal to mass times acceleration due to gravity. Our mass, remember, is not going to change. The amount of atoms that make up his body are still going to be constant, but that acceleration due to gravity on the moon is going to be less, negative 3.67 meters per second squared. So when we multiply these two quantities together, we're going to get negative 275.25 newtons. And again, we could look at our answer. Does it make sense? Well, it's negative. That makes sense because gravity is pushing us down, and the magnitude of our number is less than Earth, and that makes sense because the moon is pulling down on this person less. And that's shown by acceleration due to gravity. Right, so I'm going to give you guys a planet for you guys to work on your own. And you guys could work on it on this page because you're probably not going to have enough room. But I'm going to set it up here. And let's say we have a different person on Jupiter. And this person's weight on Jupiter is, let's say, 1,820 newtons. I want you guys to find his mass on Jupiter. What's his mass on Jupiter? I want you guys to find his mass on Earth. And finally, his weight on Earth. All right, and that does it for our target sheet differentiating between mass and weight.